this equation. By the way, what is the relation here refer for each one? First one here, this isometric constant volume, isometric process, as you see, constant volume. Second one here, adiabatic. This is adiabatic, no heat transfer. Adiabatic. This is isochoric, pressure constant. This is isothermal. This is what? Isothermal. One thing for you, the area under the curve here is referred to what? The work. This is the area under the curve, the work. This is area under the curve, the work. So there is no here area under the curve, so work is 0. Okay. Isothermal, it means temperature constant. Temperature constant. You'll find the curve here for temperature constant is higher than the curve for adiabatic. So normally here, for example, this one is referred to isothermal, and this 4 is referred to adiabatic. And what is referred to? This pressure assured pressure constant, and 3 is pressure volume constant. Volume constant. Other two meaning to be aware: reversible and irreversible. Reversible, it means can happen slowly in either direction. It means come back again to the original state. Irreversible, it means we can't back. So involves net increase in entropy. Entropy is increased. Don't forget reversible plus adiabatic, it means isentropic. And what do you mean of isentropic? That is equal to. Specific here of air increases with increase in
see both pressure and temperature. See
temperature.
okay, temperature only.
Fluid expands suddenly into vacuum through an orifice of large dimension. Then such a process is called
If a fluid
Adiab-
expands through the vacuum through resistance,
Expansion process.
free expansion,
Free expansion.
expansion.
free expansion.
Which of the following processes are thermodynamically reversible?
Throttling process. A.
No. Isothermal and adiabatic. Thermodynamic constant volume and constant pressure.
Isothermal and adiabatic.
Sir, C or E, I think. PV hyperbolic. Sir, which of the following is thermodynamic? PV is equal to C. Hyperbolic.
PV equals C.
Without mentioning
Actually,
anything.
thermodynamically reversible, isothermal and adiabatic.
Adiabatic E, okay.
Without mentioning any else.
Which of the following irreversible?
All of them both.
Throttling.
Throttling. Adiabatic no, maybe is reversible. Isothermal also maybe is reversible.
Throttling, sir, C.
Okay.
Don't care for this, no problem.
No, that's a good irreversible.
For thermodynamic process to be reversible, the temperature difference between hot body and working substance should be
Zero.
Temperature difference should be 0.
There is no such criteria.
minimum working compressor is possible when the value of adiabatic index N is equal to
What one?
1.
adiabatic index. Actually, the normal equation used for the work calculation, BV equal constant, and this is N is going to change it from 3 names. 1, which is the minimum,
Air.
1.4 in case of air, which is gamma. This is maximum, and is in between this value and this value. This is said isothermal process. This is said adiabatic process. In between is still polytropic process. Okay? So
Okay,
to
sir.
obtain minimum work is equal to 1. Molecular volume of any perfect gas at 600 multiplied 10 to the power 6 Newton per meter square and 27 Celsius will be. Actually, if you search for molecular volume, it's not easy. It's meter cube per kilogram mole. It's not easy as a unit also. So just at least write the equation BV equal N R universal T. So I give you this is meter cube per kilogram per mole per something. So it means this volume per N equal, I take this at BV, meter cube per mole or something like this. So it will be equal B, sorry, it will be RU T over B. So R is what? R universal, which is 8.314 multiply T, which is 27 plus 273, 600 multiply 10 to the power 3. You get it the finally for this one, it equal to 4.18 something like this.
4.17.
Or 175, something like this, I don't remember. At the end, the answer is first one. Okay?
Okay, sir.
A gas is compressed in a cylinder by a movable piston to a volume 1/2 its original volume. During the process, 300 kilojoule heat left the gas, and the internal energy remains same. The work done on gas in Newton meter will be
200,000. B.
internal energy here is constant.
H is equal to U plus W.
So if this constant, so it means delta is equal to 0, which is equal Q plus work. So by the way, Q is equal work. So this is 300 kilojoule. So what is the equivalent?
E. 300,000.
300,000 Newton meter. Okay. More effective way of increasing efficiency of Carnot engine is actually for efficiency of Carnot. You'll see this later at the end of the session is equal T hot below here and above is T hot minus T cold.
Decrease the temperature. Higher temperature.
Decrease which temperature?
Higher temperature.
Decrease lower temperature.
Lower temperature.
If you decrease lower temperature, so the value here for this one is increased, so the efficiency increase.
Okay, sir.
Entropy change depend on
Sir, heat transfer.
No. Changing temperature. Heat.
heat transfer. Yes. Reversible adiabatic process, change in entropy is
0.
yes,
Because it is
they give you
reversible.
the two reasons for that reversible and adiabatic both. So it means isentropic. So it means change in entropy 0. Isochoric process.
No work, see sir, no work, mechanical work is done by the system. Isochoric.
Isochoric means volume constant, so there is no work. According to first law of thermodynamics,
See sir, internal energy and B, total energy, internal energy of the system during the process remains constant. B, sir.
Total energy of a system remains constant.
B. Answer is B, sir. Option.
B.
Yeah.
D for
You
Daddy.
no, option given is B, sir, in that. Okay.
No.
Okay,
No.
sir. Okay, D.
This is definition for what?
No.
First law of thermodynamics. Energy can neither be created nor destroyed, but can
First
be
law.
converted into one form to another
Of
energy.
thermodynamics, yes.
First law of thermodynamics.
Exactly. First law of thermodynamics, relation between
Heat and work. And properties of systems. Confuse heat and internal energy. Sir, here, so either A or B. Heat and work or heat and work.
Heat work
Heat and internal energy. No, heat and work,
heat,
sir.
work,
B.
and properties of a system.
Okay, sir.
Properties B.
Change in enthalpy in closed system is equal to heat transfer if the reversible process takes place at constant.
Pressure.
Change in enthalpy. Okay, is closed system is equal to
Constant volume, no work done.
Normally, enthalpy is contact with pressure.
enthalpy pressure. Okay, sir. H.
As a thermal process, the internal energy
Constant. That's why isothermal, na, sir.
Yeah, remains constant.
constant. The change is zero. Change in internal energy in a closed system equal to heat transfer if a reversible process take place at constant.
Constant volume. Yeah.
Internal
Constant volume.
energy with volume is. First law of thermodynamics.
Mass and energy are mutually convertible. A, sir.
All agree?
Heat and work are mutually convertible, I think. C.
No, mass and energy, sir. Energy it is defining. Energy. A, sir. A. Energy can
Heat
never be.
and work,
Okay.
not mass and work. Heat and work. Total heat of a substance known as
Internal energy.
don't forget this ever. Total heat is
Enthalpy. Achha.
enthalpy. First law of thermodynamics.
E. All of the above.
Exactly. Let's see the parts for Carnot cycle. Carnot cycle actually it is 4 parts. All normally the cycles it's have 4 processes. Almost all cycles. Okay. This is some notes we take it today, but we will continue for this process and focus more for next session for power cycles. But let's see what is this notes important and valid for all. Normally all cycle we study it's have 4 process like this 1 to 2, 2 to 3, 3 to 4, 4 to 1. So 4 process. It's closed like this. This is a cycle. Second thing, anything you need to calculate it, maybe you don't see here for this type, but maybe you will see the next session for calculation for almost all types of work or heat. So for any heat calculation or for any work calculation is the difference between two enthalpies is referred to get it by difference between two enthalpies, which I mean, for example, for this case from 1 to 2 we have Qn. So how to calculate Qn? For sure this is coming from H1 minus H2, for example. Okay, so to calculate anything between two processes 1 to 2 or something like this, whatever heat or work is equal to difference between two enthalpies. This first, and for elements is a second. What else? That's it. Okay, let's see here. The four process here is two process isothermal and two process adiabatic. Okay, for the part for Q added and the Q rejected, for the part of heat happen, the process of heat, whatever added heat or rejected heat, for these two cases, this process is isothermal process. So we'll found from 1 to 2, it is reversible isothermal expansion. From 1 to 2 is reversible isothermal expansion. And from 3 to 4, 3 to 4 is the same reversible and isothermal compression of a gas. Okay. From 1 to 2, this is about for Q added, and the other one here is for Q out, Q rejected. So what is from 2 to 3? This is adiabatic, isentropic process, adiabatic plus reversible, adiabatic. So it means isentropic process from 2 to 3. Isentropic expansion of a gas. What is the advantage for this? For isentropic, delta S for this is equal to 0. And from 1 to 4 to 1, from 4 to 1 is still also it is reversible adiabatic. So, but it's not expansion here. This is compression. So this is isentropic again, isentropic, but this isentropic compression of the gas. Okay, so this is a totally 4 process. Carnot cycle, it is the ideal cycle for any cycle you need to study. This is the ideal cycle. So it means it's the maximum efficiency you can obtain. It's like a reference for you for practice process or cycles to calculate, for example, the Carnot cycle, to be aware what is the maximum efficiency we can obtain, which is not applicable, but this is the maximum can be obtained from the cycle. What is the relation for this? We write it for the previous slide. Eta is equal to TH minus TC divided by TH. What is TH? This is hot temperature, and TC is a cold temperature. So just go for any type of the Carnot cycle, apply for this equation. Normally, we calculate for efficiency and give you the hot side and the cold side. That's it to calculate. Let's see one problem numerical from the exam applied for this part of the Carnot cycle and the efficiency of Carnot cycle. In a Carnot cycle, heat is transferred as at
Constant temperature.
Constant temperature, C, sir. Yeah,
Temperature. C.
C.
exactly. Just a minute, please.
We are at Carnot cycles.
I press on the webcam. Let's back here.
C, sir. Constant temperature.
Sure.
As
Which of the following statement is incorrect?
In
Carnot
Carnot,
cycle has maximum efficiency in all cycle. Yes, is a maximum. Is reversible one? Yes. A reversible cycle has more efficiency than an irreversible, for sure. All reversible cycle has the same efficiency? No. So
first
all
one.
is maximum, yes, but not all the same value. Okay.
Okay.
Read this one and try to get it answered.
$400 minus 250.
Zero point 0.38. See.
See, sir,
See.
yeah, 0.38. 400 minus
One?
250 by 400. 0.38 CA.
This one?
Yes, sir. But maybe wrong because it is Kelvin we need.
We can use it as a Kelvin, okay. We can use it as a Rankine, okay. But use it as a Fahrenheit, not okay. So you have two options. If you don't know the conversion between Fahrenheit and Rankine, which is 460 degree, what is the other option? Going to calculator, you found it from Fahrenheit to Kelvin direct and change it all to Kelvin. Efficiency is equal T hot minus T cold divided by T hot. Okay. So this is equal. I will use it Rankine. If I use it Rankine, so added 460. So this one it would be 860 because this is the hot side. This is the cold side. Okay. And above I can use it as it is 400 minus 250. Why? Because the difference delta
Common.
F, delta Fahrenheit is the same delta Rankine. No problem. There's no problem for those. Okay. So get this answer. What is the answer?
Zero 0.17.
It's totally different answer. Okay. Understand for this?
Yes, sir. Yeah. Very simple.
Okay. Read carefully, please, and go and solve.